Hi, everybody. This is Nicole Meyer, the Digital Strategy Manager for PHCP Pros. I just wanted to thank you all for joining us today, as well as CircuitSolver, a ThermOmegaTech brand, for sponsoring this webinar, Turn Up the Heat on Legionella. Please feel free to submit a question in the questions and answers box on your screen at any point throughout the presentation. All questions will be addressed at the end of the webinar. Today's speakers will be Tom Ruggierio, Kristy Egg, and Jay Egg. Our first speaker, Tom, is the Director of Sales, Commercial Plumbing at ThermOmegaTech. He has over 35 years of experience in industrial automation, fluid power, and the plumbing HVAC industries. Tom has conducted dozens of webinars and has written several articles regarding designing and balancing domestic hot water systems. Our next speaker, Jay, began a career in mechanical design, engineering, and contracting after serving in the U.S. Navy nuclear power field. Now, as an expert consultant, he sits on several technical co-committees internationally and is currently engaged as a member of the Legionella Task Group for the 2024 IATMO Uniform Mechanical Code. Our final speaker, Kristy, is a registered nurse, public health, and epidemiology professional with a keen interest in environmental, community, and public health programs. Over the past decade, she has studied and developed a definite interest, bordering on obsession, in Legionella outbreaks in cooling towers. She now assists with water management programs, and she is quickly becoming a respected resource on Legionella-associated biofilms. And with that, Kristy, I will let you take it away.
Thank you so much. Just wanted to start by doing a little background on Legionella. As most people do know, it was actually discovered shortly after the 1976 Philadelphia Convention of the American Legion, which took place at the Bellevue Stratford Hotel, where the American Legion held its annual convention. And basically what happened was hundreds of American Legion members came and they had their American Legion convention, and everything went wonderful. It was a star-spangled bicentennial, and everybody was there. A few days after, about 4 days after the Legion members mixed and mingled, everybody went home. However, by like I said, about 4 days after, the phone began to ring with distressing news that a number of deaths of convention members had occurred. And 12 members died. 36 members had been hospitalized with pneumonia-like symptoms, some of them having had fevers of like 107 degrees. Now, many of them were older and some were smokers, but the ages of the victims actually was between 39 and 82. Now, as news began to come in, what was shown was that not all were American Legion members, some or actually their wives who had attended the conference as well. But some of the victims were like bank tellers that had worked across the street, a bus driver who had provided transportation for some of the young cadets who'd marched in the convention's parade. And of course, this prompted a huge investigation, what was going on. There was even some conspiracy theorists who thought that maybe this was an anti-war demonstration or protest. But really, what was going on here was that the CDC had launched an investigation, and what they started to find was that they didn't have an answer. They started checking everything from food to waste to anything you can think of. And basically what you had was helicopters flying in day and night and samples being taken. And of course, they were just bringing everything they could back to the laboratory, and nothing was being found. So what you have was basically the CDC getting a lot of backlash from the public. What is going on? How are these people dying? You know, just basically you had people inside the hotel, outside the hotel, neighboring hotels and buildings getting sick. So the story goes that Joseph McDade is a microbiologist, and at a party during Christmas, now of course this is, you know, the bicentennial, so this is July all the way till Christmas. So this is, July, 5 months later. He's at a Christmas party, and somebody has a little too much to drink and says to him, "Hey, what are you guys doing up there at the CDC? Why can't you figure this out?" And kind of irritates him. So he's supposed to be on vacation. Well, he cancels his vacation, goes back to the office, and just redoubles his effort. And a quote he gives is that it is basically like looking for a contact lens on a basketball court. This is how difficult it is to figure out what is going on. Well, he takes a lung tissue specimen, one of the last ones, previously unknown, and he actually finds a bacterium, an unknown bacterium never before seen. And because this guy had ticked him off so bad and he went back and canceled his vacation, we now know what is the Legionella bacterium. So that's basically the story of how we discovered Legionella. Now, here's a great kind of idea, a little pictograph of what Legionella pneumophila, which is what it's named after, of course, the Legionnaires' convention, is how we get it. Now, most people, I think, identify Legionnaires with the air conditioning system, which is actually where it was found in the hotel. But the Bellevue Stratford Hotel had a cooling tower, and it actually sprayed, and the infected water droplets rained down, which is why you had so many people get it. And most people identify it with that. But the truth is that it's mostly in domesticated hot water systems. And that's what we're going to talk about today. You can see the person there in a shower. And what happens is the infected water droplets, when you're in the shower and you breathe in, you can breathe in an infected water droplet. You can not swallow it as far as like drinking water. You can drink a cupful of infected Legionella bacteria water and nothing will happen to you. But if you're drinking and you aspirate the water, water goes down the wrong pipe, or if that happens, then you get that in your lung tissue, then yes, you can get it. But drinking the water, nothing happens. You breathe it in, aspirate, that kind of thing, sitting in a steam room, that kind of thing where you breathe in that water or infected water droplets, that's different. So what we're talking about here today is domesticated hot water systems. Now, you see the enlarged circle there on the downward left. What we're going to talk about in just a minute, because I find this fascinating, is how this Legionella pneumophila survives and how it infects other cells, because it is truly just an insidious bacteria. So I'm going to move to the next cell because I find this super interesting. All right, so you have to live this with me. So what we have here is, as you can see, this Legionella in an amoeba. And what it does is it infects other bacteria, and it kind of fools them. It's a very tricky bacteria. I'm going to go to the next slide because it gives a really interesting picture. All right, here we go. So this is a Anacanthomoeba castellani, and the Legionella pneumophila is a really singular bacteria in that it has a flagella, a single flagella, which it uses to propel itself. And it like wiggles this flagella and tells the bacteria, here I am, go ahead and engulf me. It's basically phagocytosis, where it says, go ahead and surround me and engulf me. And as it does, this larger bacteria surrounds it, and it injects this kind of like this numbing gel into it, and it paralyzes this larger cell. And as it does this, it takes over the bacterial inside, and it starts to replicate inside this larger this amoeba. And so before it knows it, before it realizes what's happening, it actually starts to replicate inside the amoeba. So by the time the amoeba realizes what's happening, it's actually become a host for this Legionella bacteria. So as it does this, it's actually using the host amoeba to send out signals to other Legionella saying, hey, come all over here. I'm taking this over. And as it does this, other Legionella are attracted. They do the same thing with similar bacteria or local bacteria. And as it does this, it forms biofilms. And biofilms are really where it's at. I don't know if you guys remember being a kid. I do. Years ago, before everybody got all freaked out, we used to run around all day. You didn't go home and sit inside and watch TV and play video games. You went outside and played. And when you got thirsty, you grabbed a hose and you drank out of it. And there was probably slime in there, but you didn't care because you were a kid. And that slime was biofilms. Well, now we think of biofilms kind of in a different way because we see biofilms and they kind of look like this. You probably saw these in hoses, but you didn't care because you were a kid. Well, biofilms now, now that we're older and we realize what they are, they cling to the inside of pipes and they form these incredible matrices because they are super strong. And unless you physically remove these, they are able to withstand temperature variations. They are able to withstand lack of water, lack of nutrients, because these wicked, incredibly intelligent Legionella pneumophila, they form these matrices. We turn off the water. If we don't physically remove them, they just stay there and they wait and they wait. And when the right temperature comes along and when we readmit water, then they wait and then they just explode and they reintroduce Legionella into the system. So as you can see this picture on the upper right, we see the secreted slime, we see the biofilm, but we see all those living Legionella under there. So when you take the water away, like the bottom picture there, the cross section, they're still alive under there. They're just waiting. And so this biofilm, one of the things that it was interesting to me about the thermal disinfection is that it's the repeated use of the hot and the thermal disinfection that you have to chip away at this. You have to constantly do this over and over again. If you can't reach all inside the pipe to physically get rid of this biofilm, then you have to do something that's going to chip away at this, because these biofilms, they are strong and they will attach in a way that's just, it is just insidious. And so we know these biofilms exist. We know whether it's a dead leg or a rarely used section of pipe, that a lot of times these chemical disinfections, they're not capable of getting to the things the way that a thermal disinfection can, because temperature is more effective than chemical means. So that's my history and a little biofilms information. Tom, you put this in.
So yeah, thanks, Kristy, and thanks for that great explanation on Legionella and biofilms. It's kind of scary the more you look at it. So this slide,
yeah.
Yes. So this slide here, basically, it's a map of the United States, and it represents the reported Legionella cases throughout the country. And what jumps out to me and probably everyone else on this presentation is that in the northeast part of the U.S., the color red is highlighted as the darkest, which has a very high rate of Legionella cases, somewhere between 2.3 and 5.1 cases per 100,000. So there are a lot of theories out there as to why that happens. Kristy, if you could just jump in for a second, kind of give us your thoughts on why you feel this is more prevalent in this section of the country.
You know what? You could not have said it better. Tom, I look at this and immediately my mind goes back to how many news articles and how many cases I've seen where VAs and assisted living facilities, nursing homes or retirement communities have been hit with Legionella outbreaks. And it's usually not cooling towers, it's usually domesticated hot water systems. And I look at this area and it's almost like there's a corridor of Legionella, and I'm looking at this and I'm just thinking, oh, for the love of Pete, what are we going to do about this? And I know that most of them are so dependent upon chemical treatment, and I wonder, why are we not looking at a different form here? Why are we not looking outside the box of constant chemical disinfection? Because obviously it is not working. So, you know, it's frustrating because I know that in this area we have just the combination of cold weather, of of constant fear of pneumonia, of flu, and we layer that upon a not working system of disinfection, we're looking at a recipe for disaster.
So thanks, Kristy. I guess the other thing is that I think you mentioned, I'm not sure if you mentioned this or not, but there is a lot of assistant living facilities in that area of the country as well.
We do. We have a lot of veterans. We have a lot of older people that live in that area. And so, we really need to look at this population that is a little bit more, needs a little bit more care. And we need to make these decisions to help make sure that their health and safety is better cared for, is better streamlined.
Right. So this slide here basically depicts water temperature effects on Legionella, and I'm sure a lot of you have seen this type of presentation in the past. And so a couple key things I want to point out here is below 68 degrees Fahrenheit, and we'll talk about cold water recirculation in a few slides, but the Legionella can survive but are dormant. The ideal growth range for Legionella is in the area of 95 to 115 degrees F. That's really the sweet spot for it. Further on down this slide here, you'll see at 130, 140, and 150 degrees Fahrenheit, different amount of times before Legionella begins to die. And the thing that's kind of interesting to me is when you jump up 10 degrees in temperature from 130 to 140, the amount of time it takes for the Legionella to die is reduced by an order of magnitude. At 130, 5 to 6 hours is 300 to 360 minutes. At 140, it's 32 minutes, which is an order of magnitude quicker. When you go from 140 to 150, it goes from 32 minutes to 2 minutes, another in excess of an order of magnitude quicker. So the disinfection range of 158 to 176, so you could imagine if you disinfect, do a thermal disinfection 20 degrees higher than the 150 at 170, the impact that would have on mitigating Legionella. And I think it would be significant. Now, the one thing I want to point out here is, which a colleague of mine frequently reminds me, that this data is basically under a laboratory environment. And so under a more real world environment, like Kristy mentioned, where you have different amounts of biofilm and things like that in facilities, these times and temperatures could basically increase over what we're showing there.
Yes, I wanted to say I know that that I took the certification class, the 1280 certification class with Dr. Stout, and Christoph Lohr was a classmate of mine, and we've talked about this. We had lunch recently, and it's so important to point out that those are lab conditions. So yeah, in real world applications, of course, time and temperature are going to vary, but that's a great guideline for time and temperature, because you always have to have something to at least start your treatment plan with, for thermal disinfection. Right. So yeah, lab, of course, standards, notwithstanding, we do know that at those temperatures, those are the rates and time for death. So absolutely, everybody has to start somewhere.
And Christoph is the one I've heard this from probably at least 10 times by now. So common theme there. So basically, ASPE has recently formed a committee. It's called ASPE-WG for Working Group 99, which was started for developing a thermal disinfection design standard. So what is thermal disinfection? Well, basically, it's a mitigation method typically or generally used as a shock treatment when a Legionella episode occurs in a facility. They'll basically flush the system with very high temperature water, say 170 F, through every fixture for 20 to 30 minutes. Now, I want to point out that not every facility flushes at that temperature or for that period of time. But I believe as our standard evolves, I think we will be settling on something more along those lines, just for the reasons I pointed out earlier with the order of magnitude decrease in time by higher recirculation temperatures. So some of the goals of our working group, ASPE Working Group 99, is to develop a design standard that mitigates the present issues associated with the use of thermal disinfection as a means of mitigating Legionella. The other goal of the design standard is to utilize current technology to automate the process, overcoming some of the present issues identified with thermal disinfection. And for your information, I just wanted to point out that ASPE has recently released for public review a new proposed standard, Engineering Methodologies to Reduce Risk of Legionella in Premise Plumbing Systems. Long title there. And I look at our Working Group 99 for thermal disinfection as kind of a subset of that overarching standard that they just released for public review. So some of the present issues that are identified with thermal disinfection is that it requires a large number of resources to implement it. The efficacy of thermal disinfection is not lasting. There's a bounce back after a short period of time. And when I get finished this slide, I'd like Kristy to jump in on that bounce back effect.
Absolutely. I'd love to.
And potential scalding issues, which obviously when you're flushing through fixtures at 170 degrees Fahrenheit, there's a real high risk of scalding. They're very dangerous. And also, if you're trying to recirculate a total recirculating system at one time and flushing through all these fixtures at one time, that could be a huge burden on the amount of very high temperature water that you require to do that. So, and obviously, or to me, if you have a very large recirculation system, it would probably be near impossible to actually provide enough very hot water to perform a thermal disinfection through the whole facility at one time. And then the other thought is that high temperature water can cause problems with plumbing components. So I just had a conversation last week with a facilities manager at a New York hospital who performs thermal disinfection on a regular basis for the last few years and has not reported any incidents of any issues with components under the high temperature water. Now, again, this is only a sample of one. Our committee will do some more due diligence in that area, but I'm not so sure that the problem is as severe as people are alluding to. So, Kristy, if you could jump in and talk a little bit about the bounce back effect with thermal disinfection and also other forms of Legionella mitigation.
Absolutely. I think it's interesting that the big war cry for people against thermal disinfection is bounce back. I as far as I know, and having served on the task force for Legionella along with Jay, there is a bounce back after every disinfection method, because the whole idea behind Legionella mitigation is that you continue to treat. And so I'm a little confused about this, because the whole idea, as far as I'm concerned, is that thermal disinfection is part of a layering and treatment operational system. And so it seems to me that this is one of those things where if you have a vested interest in your particular kind of treatment, i.e. chemical disinfection or some other kind, then you're going to cry bounce back. Well, yes, I've seen chemical disinfections that not only were bounce back, but just were ineffective. So, Jay, I know that you and I served on the task force together, and we heard this same cry as far, and also the, there's a scald fear, and it's going to ruin the piping. And we went, wait a minute. These are far cries of not wanting to even, look at this as a serious option when we knew it was effective.
Thank you, Kristy. I think one of the things, and we spent the last couple of years and developed a standard with a special task group on which Kristy and I served for Legionella standards that are considered safe for the public. Now, there's two very different parts to this, because Legionella exists for our concerns in building HVAC systems and in building domestic hot water systems or piping systems. These are two very different scenarios where if a building HVAC system becomes infected, the buildings then become buildings that can infect other buildings because the sprays go out into the open air. And those are almost always treated with chemical protocols of some sort. What we found, though, was the very peculiar and interesting dilemma of complex building piping systems and dealing with that. Because there are a couple of concerns, aren't there, Kristy and Tom, where we don't want to run chemicals through potable water systems and we can't. It was a real concern during our task group. So we really needed to join hands and lock arms with chemical disinfection for HVAC systems, and the consideration of an appropriate protocol for thermal disinfection, like we're talking about here. There's a lot. All we developed was the standards of what's safe and where it grows. Isn't that right?
Yes. And so what we did was we talked a lot about thermal disinfection for domesticated hot water and for premise plumbing, because that, to us, the safer option was to not introduce exogenous chemicals, even with this notion of bounce back, because like we said, the idea of chemicals, there was a bounce back there too. And the idea of overchlorinating systems, which also cause damage to pipes, as well as put either too much or too little chlorine into a system, which gave you either a false sense of security, or overchlorinated water, which was just as damaging to both persons and plumbing equipment. So it was kind of funny that I saw this and I thought, oh my goodness, this old adage is coming up again. So
and
I think
Kristy, if I can jump in and just say, one of the things I want to know medically, if this is, and scientifically, if this is correct, one of the things that we came to the conclusion of is that every system has Legionella. The only thing we can do is control it. It either has it or will have it. All we can do is control it to acceptable standards, right?
I think that I think that that's a pretty accurate statement, in that I think Dr. Stout once said in one of our classes that at last count that like 50% of buildings had tested positive, but whether or not it was at a rate that was infecting people. And so I think the best thing we can do is to keep our buildings as safe as possible. And I think thermal disinfection is a good system, a layered system, but a good system for doing the best possible system that we can when there's people involved.
Yes.
All right.
Thank you.
Oh, I love this one, Tom. Go ahead.
All right, so referencing our previous stated goal of using current technologies to automate the thermal disinfection process, I just wanted to show this slide as an introduction to present-day controls used for managing buildings. I'm sure everyone, or most of you, have seen the acronyms of BMS and BAS. BMS stands for Building Management Systems, and BAS stands for Building Automation Systems. They're basically one and the same, just different acronyms for the same thing. And then lastly, there's IoT, Internet of Things, which we'll talk briefly about in the next couple slides. But some of the business objectives with using building management systems is, number one, reducing operating cost, allowing you to be more responsive to service issues, leveraging experienced and skilled professionals, and then at the same time enabling less experienced or lower cost personnel to perform tasks that don't require the more experienced people. It allows you to enhance your focus on your core business activities and reduces liability. So some of the applications within a building are areas of operations management, equipment maintenance, security and building visitor access, HVAC, and plumbing systems. So just want to stop here for a second. HVAC has been integrated with building management systems for a very long time. And these building management systems have been around for over 50 years. So what's wrong with plumbing systems? I have that in red with a question mark. I see very little evidence at this point in time of plumbing systems being integrated with building management systems. And I'll talk about that again a little bit more in the next slide. And then some other applications: fire and safety systems, energy management, lighting management, sustainability and compliance, flex space management, and overall improved tenant experience. So why the world is moving towards smart plumbing? I think we should really actually relabel that slide and basically say, why is the world slowly moving towards smart plumbing, or why should the world be moving towards smart plumbing systems? Because right now, at this point in time, it's not really that prevalent. So as the building management systems are evolving, they're basically trying to drive to improve operational efficiency, comfort, patron safety, sustainability, and risk and liability management. I never thought of this, but go ahead, Kristy.
I think you're right. I look at this and I think, for something as important as plumbing and something as important as public health, smart plumbing would be something that would almost seem like second nature to put on a smart controls feature. So it would seem like this is something that somebody would have thought, hey, this is a good idea. This should be something that we should automate for water savings, for power savings, for just a controls feature. And the amount of time and effort that's been put into controlling waterborne pathogens and public health, I can't believe that this is not something that's already been kind of, scooped up and automated.
Right. So again, in our thermal disinfection WG99 committee, we've basically been talking a lot about using automation as a way of evolving the thermal disinfection process. So the other thing here, just to kind of close out on this slide, is that the restrooms is the kind of the last frontier for building management systems due to the privacy concerns in the restrooms, and also a lack of applicable technology, which is rapidly changing. That area is changing. And restroom water usage is something that we should be focusing on, because it represents a high percentage of all the water used in commercial buildings. At the bottom right of this slide here, you see for office buildings, hospitals, hotels and motels and schools, the water usage is in those areas is 30 to 45%. So there's a lot of water usage in the restrooms in these types of facilities. So what's in it for me? Why should I basically integrate a plumbing system to a building management system? Well, there's definitely cost savings associated with it. You're saving time. Time is money. And by saving money, you're actually making money. So that's one area. And then the other area is obviously superior performance. You have healthier facilities. Because of all the data you've been gathering and taking advantage of, you'll be better for compliance and reporting. And it'll just make everyone's life a little bit easier. So, and I think we touched on this a little bit briefly, but maybe, again, Kristy or Jay, if you just want to jump on this real quick. I mean, we kind of don't have a whole lot of time left, but, we talk about thermal disinfection versus chemical disinfection in the U.S., but in Europe, it's the prevailing way of doing Legionella mitigation. If you guys could touch on that real quick, I'd appreciate it.
Absolutely. I've reached out to some of my contacts over in Europe and told them that I was doing this, and they all said the same thing. It's it is the way they do their domesticated hot water and their premise plumbing disinfection, because they are very hesitant to add chemicals unless it's absolutely warranted. It's the most widely used method, just like it says in the quote on bottom right. Thermal control is still the most widely used method for preventing Legionella in hot water systems. And I think, it's for them, it's all about public health. It's all about safety, and it's all about the fact that it works for them. I was kind of confused on why they kind of laughed at me when I said that I was reaching out to them. They said, well, it works. Why wouldn't we use it? It's something that we stay on top of. We constantly monitor it. We measure it. And I said, well, what about a scald fear? And they said, well, no, we use, the mixing valves. We make sure that, people know that we use a thermal disinfection. They know not to do it. We tell them we're doing a thermal flush. And I was like, oh, okay. And they said, well, and then it was very funny because one of my British friends said, well, we don't sue like you do in America. I said, okay, fine. I said, well, that's true. Okay. And so, but that was just funny. And he was just poking fun at me because we kind of have a British and American thing going back and forth. But it's very interesting to me that they use it constantly, and it's just such a known, useful, thermal disinfection is just the way it's done over there, and that we're kind of looking at it like, oh, well, what a novel concept. And they're like, okay, get on board. So I just thought it was very interesting that they're, like Denmark, that's all they do. That's, for them to put chemicals into something that can be done with thermal disinfection is just such an outlandishly stupid concept that they just, why? And here we are going, well, should we not? And they just kind of look at us with this big question mark over their head. So I wanted to put these in here because I just wanted to kind of, counterpoint. It does work. So just thought I'd add that just for conversational properties.
And here's the thing. We don't, if I can just add a quick 30-second blurb, as citizens, consumers in the U.S., we have not seen like a huge outbreak of domestic hot water Legionnaires cases. And the reason why, you got to think about this. If you drink it, as Kristy said, it's not going to affect you. Really, where this is important is especially with our aged population, because what is the mortality rate again for somebody that catches Legionnaire's disease in the general public versus assisted living facilities? It goes up dramatically for mortality, yes. Right, Kristy?
Well, yes. We also know it's incredibly underreported, but we do know that as far as already being hospitalized or already having a comorbidity, that it goes up 25 to 34%. If you already, if you catch it and you're already in a healthcare facility, then yes, then obviously it goes up quite a bit. However, if you get it and it's like if it's an outbreak as far as a cooling tower, then we get more cases because it's a larger geographical area. But we do see them in domesticated hot water, premise plumbing instances where there are cases and we do have deaths. So the point is that we just need to come to grips with the idea that thermal disinfection does work in those cases, because there are a lot of those cases. They're just not as media attention grabbing because the geography isn't as great.
Until we have and this will happen, this is why it's important to do it now, like our friends in Europe, until we have this big expose on how could we not have been doing this for the last 30 years, thermal disinfection. And I can see the headlines now, it'll say we could have started integrating this. And that's exactly what Tom is doing and you are doing with standards. And so is Christoph Lohr and IAPMO is very much engaged in this, but we're trying to get standards for this prior to a lot of people, reporting that why haven't we been doing this? We could have saved lives, right?
And that's what that ASPE 99 is good for. Now, this is a great chart, and I know you're going to say, Tom, and I know you're going to say this, but I don't care that it's back in the 80s. But you know what? To me, that just means we've had this information since the 80s and still haven't used it in the way that it should have been applied. So go ahead.
No, so that was a great introduction. Thank you. But again, as Kristy mentioned, and she knew I was going to mention it because I guess I'm in some ways apologizing. This information was basically from the late 70s, early 80s. This was at a VA hospital in Pittsburgh. And Janet Stout, who you heard us talk about it several times, Dr. Stout basically was involved with this research. But basically in 79 and 80, you can see all these cases of Legionnaire's disease that were reported at this hospital. Almost on a monthly basis, there were more cases of Legionella being reported, 79 and 80. Midway through 81, they performed, I believe it was the first thermal disinfection Legionella mitigation method. And the blue arrows pointing down is basically when that thermal heat and flush, which they called it then, was instituted. And as you can see, these red lines indicate positivity rates of testing certain distal sites at 30%, greater than 30%, or less than 30%. And briefly, what you can see here is every time a thermal disinfection was done, the positivity rate dropped, and also the number of cases for Legionnaire's disease dropped. And so they would test on a monthly basis, and then once the positivity rate got above 30%, meaning I think they were testing 10 fixtures, if 3 or more than 3 fixtures basically tested positive for Legionella, they did a thermal disinfection. And as you can see in 82, the more often you did it, the more the cases went down, and then also the positivity rate went down for longer periods of time. So I think this supports what we've been saying all along, is that if we can take thermal disinfection, instead of just making it as a reactive shock treatment, but make it more as a proactive event where you're doing it on a periodic basis, I think that would be a great solution to mitigating Legionella. And as Kristy said very early in this presentation, you have to eat away at these biofilms. So if we were doing whatever the period ends up being, every month, every 2 months, whatever, we were doing thermal disinfection at 170 degrees for 30 minutes, I think we'd have make a big impact on cutting into these biofilm issues. And over time, they would become, I don't want to say non-existent, because I don't think that ever can happen, but they would become a lot less severe.
Absolutely. I think this needs to be, as we've talked about, part of a water management program. And I think that's something that needs to be looked at. All right. Now you have a very interesting product that I really wanted you to be able to talk about, because we talked about the IoT support as far as getting, smart automation in buildings. But I know you have a product that I'm super excited for you to talk about, because I absolutely love it. Your thermal disinfection valve. Yeah.
So we'll jump ahead. I'll just take a couple of seconds on each one of these next couple of slides. One is the Internet of Things is basically just the next evolution of intelligence in building management systems. It's basically networking capability, smart sensors, wireless connections, and things like that. So that's something that we'll take a look at when we're doing our thermal disinfection standard. And obviously, as all the advantages I pointed out to building management systems, the same advantages with IoT systems. So what Kristy wanted me to get to is we have 3 products, and we have a few minutes left. We have 3 products that we may only have time to talk about 2 of them that ThermOmegaTech has for supporting Legionella mitigation. So the first one, which I think Kristy seems to be most excited about, is our normal CircuitSolver valve. And most of you out there hopefully have heard of CircuitSolver, which is a thermostatic balancing valve for domestic hot water systems. This valve here is the CircuitSolver Plus. It also has thermal disinfection capability. So this valve basically has 2 thermostatic actuators built into it, one on the left-hand side of the valve and one on the right-hand side. The actuator on the left-hand side, and we have a little simulation I'll show you in a minute, but the one on the left-hand side basically does your normal, say you're recirculating at 140 degrees normally, that would balance the system out at 140. The actuator on the right-hand side is if you then induce a thermal disinfection situation, the valve on the left-hand side, the actuator on the left-hand side goes full open and allows the water to go through at 160 to 170, and basically that actuator on the right-hand side starts balancing the higher temperature water, so that now when you're doing a thermal disinfection, you're balancing that water so that all the water doesn't go through the path of least resistance, that all the branches or risers that are being thermally disinfected basically get their fair share of hot water. So it's not all going to one place. So here's the simulation. Unfortunately, I can't stop the simulation and point to different things here. So this is going to constantly be running. But basically, the background color represents water temperature. So blue is cold water. Green is warmer water. Yellow is water, higher water, and then orange and red. So basically what you see is when you're in the orange and red range, the actuator on the left-hand side basically is fully open beyond its port that's there in the cutaway. And the actuator on the right-hand side starts balancing the hot water. So again, this is constantly going through the cycle. So now we see blue, and basically you'll start seeing the actuator on the left-hand side opening and closing, balancing to the 140. And then as time goes on, the thermal disinfection effort this happens. And now you see the water going from yellow to orange to red, meaning that water temperature is now getting to 170. And now you see the actuator on the left not moving at all, and the one on the right is now balancing the system. So basically, it has enough smarts in it that it recognizes when you see very high temperature water, and it will start balancing that so that you don't basically waste any water, and you basically make sure that everybody's getting what they're looking for. So that's that one. And if anyone has any interest in seeing the simulation or having me sending it to them, because we're under a time constraint right now, I will definitely send it to you.
It's absolutely brilliant.
It is, isn't it?
Yes.
I can see why I love it.
Yeah.
So, and then next, again, I know we only have a minute left, but so next, we have just introduced recently what we call, and Kristy, I'd like for you to comment on this, and Jay as well, after I get done my little presentation with it. But this is what we call a cold water valve. Internally at our company, we call this type of valve a reverse acting valve, because the normal CircuitSolver closes on warming temperature water. This valve closes on cooling temperature water. So this valve is very good for balancing cold water systems, recirculating cold water systems. And so you'd say, well, why do you want to recirculate cold water systems? Again, there's a lot of proponents against it. They're saying there's not a lot of evidence of people acquiring Legionella based on cold water systems. I think that's really a myth. I just think that people aren't really looking for it, but it happens. So what are some of the reasons why you would recirculate cold water? One is in cold water systems.
Go ahead. I thought you were, it's rhetorical, please.
Yeah, no, in cold water systems, you have a lot of stagnant lines for low usage, and you have a lot of dead legs and things like that. So what happens with those situations? You basically have bacteria and waterborne pathogens that tend to grow. You can have groundwater temperature that in certain areas of the country gets pretty warm, and then you have heat gain in these water systems. So now you could be having water highly into the Legionella growth rate area. Also, with stagnant lines and dead legs, you're not basically taking the residual chlorine and moving it, distributing it evenly throughout the system. So you need to keep cold water moving in these branches to basically get the residual chlorine distributed equally, to get the temperatures equal throughout the system so that you don't have these hot spots and things like that. And there also is a VHA 1061 directive that basically recommends for VA hospitals, when possible, to recirculate the cold water. To date, we've done 3 VA hospitals by recirculating the cold water. We have a couple more on the books. We've also had some inquiries from some major hospital chains as well as some hotel chains inquiring about cold water recirculation. So if Kristy or Jay, if you want to kind of comment on the need.
I do want to comment because Kristy and I ran a mechanical engineering and contracting company for many years, which means we could do full plumbing systems as well as the HVAC systems. And the events where you end up with 95 plus degree cold water coming through your faucets is actually very common, a lot more common. And this is one of those scenarios, once again, where we all know inherently that stagnant water in cold water lines has an opportunity to grow. this grow Legionella and other bacteria. And I'll leave it there. It's just an obvious thing. If we don't take care of it, we're going to be paying for it later.
Right,
I love
thank
it.
you.
Great reasoning for both of you. Tom, excellent job on this. And you know how much I love this one. I love your next one. I want you to get to it because I love it. I love the tempering valve.
Okay, well, we'll give it a shot then. So,
You got it.
so this, so we call this a DTV, a drain tempering valve. Basically, the top part of the valve you see here is silver. That's stainless steel. That's our thermostatic paraffin wax actuator. The bottom of the valve is a cold water inlet. This is used in situations, if we talk about thermal disinfection, once you finish a thermal disinfection cycle, now you have your hot water system with sitting there at 160, 170 degree water. I'm sure you probably want to get rid of that and replace it more with the lower temperature water that you normally use for the plumbing system. So that water has to go down the drain. Well, by code, you're not allowed to have water go down the drain of higher than 140 degrees Fahrenheit. So basically, the purpose of this valve is to sense the effluent temperature of the water. If it's higher than 140 degrees Fahrenheit by code, the bottom of that valve opens up. It's a cold water inlet, and it basically mixes cold water with the effluent, mixing it down the drain to under 140 degrees. So in places like hospitals where you have sterilizers, autoclaves, steam humidifiers, all those types of situations where you have very, very high temperature effluent, this valve is a great way to temper that water before it goes down the drain and performs the code. There's a lot of other ways out there to do that, but they're a lot more expensive. They take up more space. They have electronics associated with them, so you need an electrician for an installation as well as a mechanic. So a lot more complex and a lot. This kind of checks all the boxes. So these are a couple just different ways of basically implementing the system. The first one on the upper left shows our actuator in a horizontal position. The effluent comes down vertically over top of it. And as the water temperature is higher than 140, the cold water inlet opens up and basically mixes it down. Now, once this gets satisfied, our valve closes, and now you have essentially what's almost like a non-compressible fluid water, basically being shut down as it's flowing through from your backflow preventer. That can produce a big pressure spike. So what we require is also a water hammer arrestor in between the backflow preventer and our valve, which will take out that shock. We've seen some cases where without having that, we get premature failure of our valves because of that shock. So that's basically it. I think we're done now. I appreciate everybody's time and patience and listening in on us today. It was our pleasure presenting this to you.
Absolutely, Tom. Great information and some great products. I am absolutely thrilled to have been able to do this with you, and thank you so much for your time.
Thanks, everybody.
Thank you.
All right. Thank you, Tom, Kristy, and Jay, for that great presentation. For all attendees, there's still time to submit your questions in that questions and answers box on your screen. It looks like we've received a few already, so I will officially kick off our session here. Let's see. Domestic water distribution is limited to 100 degrees Fahrenheit for hand washing, sinks, showers, etc. In order to circulate such a high temperature for thermal disinfection, a point-of-use thermostatic mixing valve would need to be installed at every fixture. How has this been achieved in other large hospitals, particularly with older infrastructure?
So I'll give this one a shot, Nicole. So basically, when you're doing the high temp flush for these systems, the goal is to actually flush that high temperature water through the fixtures. A lot of cases of acquired Legionnaire's disease originates from Legionella being detected at the fixture. So you have to flush through the fixture. So when you're doing a thermal disinfection, and there are products out there now, smart faucets and point of use mixing valves that will allow you to, when you're doing the thermal disinfection, basically to bypass that valve and basically flush through the 170. So basically, that's how it's been done. You still have to flush through the fixture. You just have to have the right componentry to be able to bypass point of use mixing valves when you're doing the thermal disinfection.
All right, thanks, Tom. Let's see. We had another one here specifically for you. Kristy, J, and Tom, thank you for the presentation. It was very informative. I designed both HVAC and plumbing systems, and I agree there's a disparity between the two groups as far as taking advantage of the technology available today. This question is for Tom. What do you suggest to the plumbing community as far as getting on board with using newer technologies?
So first of all, thank you very much for the compliment, Kristy J, and I really appreciate it. Hopefully I didn't paint too bleak of a picture when I'm talking about the lack of using current technology in the plumbing systems. I do see some light at the end of the tunnel. My feeling would be to start off by investigating sensing devices for pressure, flow, and temperature, which all three of them are very important in plumbing. Everyone is interested in data these days, so start off by maybe you doing a Google search or whatever for sensor technology. Find manufacturers of products that may be of interest. It could be electronic flow meters, electric temperature sensors, or pressure sensors. Find the devices that can be easily interfaced to building management systems or building automation systems, because that's where the interface is going to happen. That's where the data is going to be gathered. So, and then if you have an electrical department in your firm, basically work with them and, come up with some solutions and offer them to the building owners that are already have BMS systems in place. I am sure they will find ways to use them. So I think that's a good start, is basically starting with the sensing end of the newer technologies that are out there.
All right, great. Next question here. Our research indicated that the normal chlorine chloride addition to municipal water, 0.05%, is 100% effective to kill all Legionella and others. Does it make any sense to use high heat in areas with properly treated and monitored municipal water systems?
So when I saw that question, and Jay or Kristy, if you have comments on that, you can definitely jump into it. But when I saw that question, it kind of reminded me of the certification class that I took a few months ago. You heard us mention about Dr. Stout. Dr. Stout has probably 40 plus years experience with Legionella mitigation, different forms of mitigation and stuff like that. And so I remember her talking about this, and I jumped to our training manual that we have for certification, and I can send this to you, but I guess, and believe me, I have nowhere near the expertise of Dr. Stout, but I'm just kind of read off to you real quickly what was in the training manual we had relative to using chlorination as for continuous disinfection. So on the pro side, basically she states that it's freely available, special equipment is needed, and regulatory agencies deal with this often, so they're familiar with it. On the con side, she says it will not adequately penetrate biofilm, can cause pipe corrosion, byproducts are carcinogenic, the Legionella can be resistant up to 50 milligrams per liter, possible extended time for efficacy, and impacts water quality, taste, and odor. So basically, I'm kind of like the messenger here. I'm not the expert in this area. I'm just telling you what Dr. Stout said. So any studies that you have that basically reflect on the advantages and the success you're having with that, I think would be great for us to see, and also to share with the rest of the community and our task force that's charged with creating the standard. But again, I'm just kind of reiterating what I've heard from her. So you evidently you have a different experience, a different level of success with this. So maybe we can put our heads together and figure out where the differences lie.
All right, great. Next question. Let's see. A few on circ pumps. Should we utilize a time clock on the operation of the circulation pump? And following up with that, should the circulation pump run 24 hours a day?
So this question comes up a lot in a presentation I make for ASPE. And there's two schools of thought here. You have the energy code, which says that you basically have to have some type of an aquastat, some type of a timer, some type of method of shutting down the pump when you get to your desired return temperature. But if you talk to anybody in the world of Legionella or healthcare or OSHA, especially, they all have a totally different opinion on that. They feel that the pump should be running 24/7. You don't want to basically shut down the pump and have opportunities for temperature changes and things like that in areas where lack of flow and Legionella growing. So again, there's always these two schools of thought. You have the energy code, and then you have OSHA, basically at kind of at odds with each other. And generally speaking, what I've heard is from the engineers that do in the design, they'll put these aquastat systems in there, but they'll actually, and probably none of them will admit it, but they'll actually bypass them and they'll be recirculating the water 100% of the time. So I'm not sure if that answers your question or not, but I'm just letting you know that's kind of what kind of goes on out there.
Another thing, if I may add, that you mentioned it early on, we have too long treated plumbing systems as dumb systems that aren't on BMS. And the question of timers and whether it should go 24 hours a day is very, very clearly controlled and answered by getting the plumbing system up to the 21st century, so to speak, right?
Yep.
All right, so we're receiving a lot of questions. I think we'll just do two more quick ones here to wrap things up. Let's see. Is there a difference in buildup of biofilm on, for example, copper versus PEX versus CPVC?
Kristy has some good answers on this. Oh, you got it. Go for it.
Yeah, I'll just do a quick little answer from what I understand. One is that initially, when you have a new system, I would say that my understanding is that like the PVC or PEX is more resistant to that. But once the biofilms start forming, then they're all kind of equal at that point. Jay, or Kristy, you have something to add to that?
Well, I do, and I don't know if Kristy is on the same track, but the copper pipe folks have some pretty solid data showing that copper is more resistant to biofilms. I do know that, but I can't cite that. I don't have the reference in front of me.
All right, great. And this may be a good question to wrap up on. The ASPE Working Group 99 Committee for creating a thermal disinfection design standard seems very interesting to me. Is there any opportunity to become involved with it?
So, fortunately, we have formed a very strong team with a lot of experience in all facets of plumbing systems, especially as it relates to Legionella mitigation. But that being said, we have a couple of members that for one reason or another are finding it difficult to participate on a regular basis. So we'll see how that works out with them in the near future. I would suggest that you or anyone else that's asking the question or anyone else out there, if they have any interest in being part of this ASPE Standard 99 for thermal disinfection, you have my contact information there. Please reach out to me and I can send you an application, and then you can fill out the application. And then if people start falling off, a couple of people just don't have the time, then definitely consider adding some other candidates for that.
All right, great. Well, with that, I think I'll close out our Q&A session. There were a few questions we don't have time to get to, but we will do our best to follow up with you individually over email with responses. So thank you once again, Tom, Kristy, and Jay for that wonderful presentation. Let's see. I would also like to give one more thanks to CircuitSolver, a ThermOmegaTech brand, for sponsoring this webinar. And of course, thank you all for attending as well. All attendees will receive an email from us with more information on how to access a recording of this webinar, as well as an optional survey where you can let us know your thoughts. For any questions, you feel free to also email me at nicole@phcppros.com, nicole@phcppros.com. If you're interested in attending more of our webinars, you can find details on our 2023 library and what we have currently scheduled on www.phcppros.com/webcasts. On our website, you can also subscribe to our e-newsletter so you never miss hearing about a webinar you may want to attend. Thanks again for joining us and have a great day.